Evening, guys. Am I audible? Yeah. So we'll get started. So today we'll get started with the 12th chapter, that is atoms. Okay. Before that, any doubt from the previous chapter, that is dual nature of radiation and matter? Can I take that silence as no? No doubts? At least say yes or no.
No, sir. No doubts.
Good. So chapter 12, write down the heading as atoms. So this chapter is basically a recap of atomic structure, which you have learnt in your chemistry last year. Okay. The only difference is there you would have not seen what is the mathematical reason behind a particular formula to be derived. Here we'll be deriving those things. Okay. And the basics are still going to be in the same fashion as it goes in chemistry. So we'll get started. The topics that are covered in this chapter are, first we will see what is the introduction. Okay. Then we'll see what is alpha particle scattering and Rutherford's nuclear model of atom. Then we'll see what is atomic spectra. Spectra is plural of spectrum. Then we'll see Bohr model of the hydrogen atom. Then we'll see the line spectra of hydrogen atoms. Then de Broglie's explanation of Bohr's second postulate of quantization. This is the same concept which we discussed yesterday, right? That lambda is equal to h by mv is there, no? It is the same concept which gets repeated in this chapter as well, just to give you an extra support of the Bohr's quantization condition. Okay, now see. So if we have to begin with this chapter, the concept of atoms, like we are going to learn a simple structure, something like this. First, when you talk about an atom, right, there are different structures that were proposed and they try to give a theoretical explanation for the stability of those atoms, but some succeeded, some failed. That's a different story, but that is what happened, right? So if you see the basic introduction, generally if you take at atmospheric pressure, then you can say air and other gas molecules are generally pure conductors of electricity. So what do we mean by pure conductors of electricity? They don't get ionized, right? So this is because they do not have free charge particles. When they have free charge particles, they tend to get ionized, right? But whereas here it doesn't get ionized. However, when you pass the electric current through a gas, if by some mechanism, then what can happen is you can create those charged particles in those gases. So this can be done in many ways. One of the ways is by applying a large potential difference across a gas column at a very low pressure. That is one of the methods. Or you can create an ionization process by allowing the X-rays to pass through these gases. Okay. Then what happened later? The study of electric discharge through gases gave valuable information to us regarding the structure of atom. This led to the discovery of electrons, the concept of electrons by a scientist named Thompson, and later on to the discovery of X-rays by Röntgen. Okay, so this is what happened. This is a basic introduction. So where did the idea come from? If you observe it under normal atmospheric conditions, if you see air and other gas particles, they are very, very, very bad conductors of electricity. They're actually poor conductors of electricity because they do not have free charges. Right? Now, based on this concept, there were different atomic models that were proposed to us. So initially what happened, when you go back to 1803, Dalton was an English teacher who explained or who mentioned saying that matter is made up of extremely small particles called atoms, means they are indivisible particles. So the smallest substance that you can find in nature was atom according to Dalton. But later came the discovery of these electrons, protons, and neutrons, which led to the concept of subatomic particles. Okay. Then what happened? Prout in 1815 suggested that all elements are made up of atoms of hydrogen. Okay. Then, so this is how the evolution took place. At that point in 1803, when the concept of this atomic structure was not there, the first proposal was made by Dalton saying that atoms are indivisible particles. This you would have learnt in your lower grades. Then what happened? Prout was a scientist in 1815, suggested that all elements are made up of atoms of hydrogen. Okay. Since many of the elements were found to have atomic weights that were not the exact multiples of that of hydrogen, the suggestion that Prout gave was not accepted. Okay. Since many elements were not found to be of the atomic weight, since let's say Prout suggested that all elements are made up of atoms of hydrogen, what should have happened to the other elements? The other elements should have had the atomic mass, which is exactly a multiple of the atomic mass of hydrogen. But that didn't happen. Why? That's what we see in today's discovery, right? In periodic table, that is what we understand. So after the discovery of radioactivity and the concept of electron, interest in the study of atomic structure increased, and many models of atoms were suggested at different times. Okay, at different time periods, different models of atoms were proposed. That is what we are going to see, what was the proposal made and why that particular proposal failed. So to begin with, first we are going to see the Thompson's atomic model. This says, from the study of discharge of electricity through gases. Okay, when you take the discharge of electricity to gases, it became clear that an atom consists of a positive and a negative charge. Right? Then what happened? Thompson tried to explain the arrangement of positive and negative charge of the electron inside the atom. So basically what he told is, according to him, an atom is completely a sphere of positive charge having a radius of about 10 power minus 10. So he told that, according to him, atom is a sphere, okay, accepted, of completely positive charge, and the radius of that sphere was found to be how much? 10 power minus 10 meter, and the positive charge is assumed to be uniformly distributed over the atom, right? That is distributed over the sphere, and the electrons are embedded inside the sphere between the positive charges. So that is it. Since it looks shape of a watermelon, like how the melon red color part will be there, and seeds will be distributed throughout it. The red color part was treated as the positive charge of that atom, and the seeds were treated as the negative charges. So that's why you can either call it as watermelon structure or plum pudding model also. You would have heard this. So this Thomson's model of atom was also called as plum pudding model of atom. Right. Then, so this was the structure that was proposed by him. But it is not the structure that is important. You need to explain the stability of it also. So then what he told is the total positive charge inside the atom was equal to the total negative charge carried by the electron, due to which the atom was considered to be electrically neutral. That is another point that he mentioned. Then he told, in general, the electrons of an atom are located in symmetrical pattern with respect to the center of the sphere. So there's another point that he mentioned. Okay. But unfortunately, what happened? There were certain drawbacks. So actually, this is how the atom looks like. The electrons are embedded inside a positively charged matter. So the drawbacks that were associated with Thomson's model of atom is, if you go back to the concept of electromagnetic theory, the vibrating electron should radiate energy, and the frequency of the emitted spectral line should be the same as that of the electron. So what should happen according to the electromagnetic theory? If you have a vibrating electron, what will it do? If an electron is an oscillation, that's what we learned in electromagnetic waves. So if you have an accelerated charged particle, what does it do? It starts continuously radiating energy, and that energy will have a frequency associated with it. Then the frequency of the emitted spectral line should be the same as that of the electron. So in the case of hydrogen atom, Thompson's model gives only one spectral line of value 1300 angstrom. Its wavelength was 1300 angstrom. But what happened? The experimental observations that are done in today's world, we know that the hydrogen spectrum consists of 5 different series with several lines in each series. You would have heard these things: Lyman series, Balmer series, bracket series, Passion, and Fund series, right? So these are all the 5 spectral series lines that are emitted by the hydrogen atom. But according to the Thomson's model of atom, what should have happened? There should have been only one spectral line. So this was one of the reasons why this theory was not accepted. Secondly, it failed to account for the scattering of the alpha particles through large angles. So we know that alpha ray scattering experiment was done by a scientist named Rutherford, right? So according to Rutherford's experiment, this model failed actually. So which we are going to see in the next subtopic. Is it clear till this point, guys? Is there any doubt?
No, sir.
Okay. Now what I'm going to do is I'll proceed to the next part. So now we are going to see the alpha particle scattering experiment. Okay. So explain the experimental arrangement, observations, and conclusions of Rutherford's alpha particle scattering experiment. So Rutherford, along with his associates, he studied the scattering of alpha particles by using a thin gold foil in order to investigate the structure of the atom. Okay. So basically what happens, you have an alpha particle, which is a positively charged particle having mass equal to that of helium atom and positive charge and magnitude equal to twice the charge of an electron. Basically, an alpha particle is a byproduct of a radioactive element's disintegration. Okay. So what is an alpha particle? It is a positively charged particle whose mass is equal to that of helium atom. 1 minute. And it is positive charge in magnitude, which is equal to, so, twice that of the electron. So helium 2 plus nucleus is what is called as an alpha particle. And how are they emitted? They are emitted by many radioactive elements. So the scattering of alpha particles provides useful information about the structure of atom. That is what we are going to see now. So let's see what is the experimental arrangement. So we have a fine pencil of alpha particles which were obtained from a radioactive material. So you have a radioactive material. From those radioactive materials, what happened? There were alpha particles that are coming out, and those alpha particles were diverted through a very small opening. Remember, this radioactive element was placed inside a lead box. The reason why lead box was used is because lead does not allow these alpha particles to penetrate through them. So in order to ensure that you have only some alpha particles coming out of a small opening was created in the lead box, and that's what is given here. See, a fine pencil of alpha particles were obtained from a radioactive material like radium or radon by placing it in a lead box with a narrow opening as shown in the figure. Okay. Once this comes, the alpha particles are emitted from the source in all possible directions, but only a narrow beam emerges from the lead box because of the small opening. The remaining alpha particles are absorbed within the lead box itself because lead does not allow alpha particles to penetrate through them. So what you will do is you will pass these alpha particles through diaphragms D1 and D2 and a narrow beam of alpha particles incident on a thin gold foil. So you have a thin gold foil, and these alpha particles were made to fall on that thin gold foil. Then what happened is the alpha particles started scattering through different angles. Okay, so why did this happen? One point we need to understand is alpha particles are already positively charged particles because they lose 2 electrons to gain that positive charge of 2 plus. So when these particles are going and falling on the screen, why is the scattering taking place? That's what we need to understand. Okay. So the scattered alpha particles, what they do, they strike a fluorescent screen which is coated with zinc sulfide. Okay. So when the alpha particles strike the screen, tiny flashes of the light were produced on that particular screen. Then the observations can be made with the observations of all these things can be made with the help of a power microscope, low power microscope. Okay, so this is all about the experimental setup. Is there any doubt from this? Is there any doubt from this?
No doubt, sir.
Okay. So once this setup was done, the observations were now made. So what did the observations say? Most of the alpha particles either passed straight through the gold foil or were scattered by only small angles of the order of few degrees. So what happened? Most of the alpha particles either passed straight through the gold foil or were scattered by only small angles of the order of few degrees. So this one is helping us to eliminate the atom that was proposed by Thompson. Why? Because when will those alpha particles be able to pass through the thin gold foil? Only when most of the atom is empty. Right? Because what did Thompson say? Thompson told that most of the complete atom is positively charged. Had it been positively charged, none of the alpha rays could have penetrated through the atom itself. Right? So this observation led to the important term as a load, as a lot. Sorry. This observation led to the conclusion that an atom has a lot of empty space. Okay. Then what happened? Few alpha particles were scattered in the backward, which led Rutherford to conclude that whole of the positive charge, instead of being concentrated within the atom, it was concentrated at a tiny space whose was about 10 power minus 14 meter. And this was the first time there was a name coined as nucleus. The region of the atom where this positive charge was said to be concentrated was called as nucleus. So at that point, when Rutherford introduced nucleus, it was only known that nucleus consists of positive charges. But in today's world, we know that nucleus consists of positive and neutral particles. So it is positive charge for sure. That is, it contains protons, but along with protons, it also has neutrons. So, but at that point, when nucleus term was coined, it was known that it had only positive charges. Now the question is, the atom is neutral. Then where are these electrons? Right. Now we'll come to that. So only a small number of particles approached the nucleus of the atom and they were deflected at very large angles. So this is the observation that was done. So what happened? The two important observations is the alpha rays, most of the alpha rays passed through the gold foil without scattering, right? Which concluded that the atom as a whole is empty, right? Atom has a lot of empty space and few alpha particles started getting scattered in the backward direction, which led to the conclusion that whole of the positive charge was concentrated in a tiny space of 10 power minus 14 meter. Okay, this region of atom was named as nucleus. Now comes an important point. We need to see a term called as distance of closest approach. The name itself is suggesting there is a particular distance till which these alpha particles are able to travel before they take a very big turn. Right? So when an alpha particle is directed towards the center of the nucleus, we know that nucleus is positively charged, will close up towards R naught shown in the figure above, where its kinetic energy will up the static trying to say is if the alpha particles are traveling, then the alpha particles will be able to travel till a certain distance towards the nucleus before they take an exact 180-degree turn, and that still they are able to approach and the distance in the nucleus is what we call it as R naught, and R naught is what is called as the approach. So in this distance of closest approach, what happens is initially the alpha particles had kinetic energy. This kinetic energy gets converted into electrostatic potential energy. So when this kind of a conversion takes place, the alpha particle will begin to retrace its path. And the distance R is known as the distance of closest approach. Now, let's say if m and v be the mass and velocity of the alpha particle directed towards the center of nucleus, the kinetic energy of the particle is half. Since the alpha particle is 2 nucleus is e, where z is the atomic number of the nucleus, the electrostatic potential of this alpha particle when it is at distance r naught is given as 1 by 4 pi epsilon naught. That is k q1 q2 divided by r naught. So q1 is 2e and q2 is ze divided by r naught, where z is the atomic of the particle and epsilon naught is the. What is happening? The electrostatic potential energy is exactly equal to the kinetic energy, because that is the kinetic energy is the one which has got converted into electrostatic potential energy. So 1 by 4 pi epsilon naught into 2 into Z divided by R naught will be equal to half mv square. R naught is equal to 1 by 4 pi epsilon naught 4 divided by mv square, and this is the formula for the distance of closest. Is it clear, guys? Is it clear? Is it clear or not?
Sir, what exactly is R naught?
R naught is the maximum. See, did you understand this concept? No? The alpha particles are traveling towards
Yes,
the nucleus,
sir.
correct? Are they colliding with the nucleus? Are they going and touching the nucleus?
No, sir.
No, right? They will be able to approach till a certain distance. Let's say at this point. So I told you about this thing, no, something like stopping potential. So what you have, positive charge. If the helium 2 plus is positive charge, nucleus is positive charge. So two positive charges are approaching close towards each other. Will there be a possibility for them to touch each other naturally without an external force?
No, sir.
Logically, all right. So it will be, let's say, this nucleus is at its position only, but this alpha particle is the one which has kinetic energy because it is traveling. So initially, it would have had maximum kinetic energy, correct? As it is approaching towards this thing, as it is approaching towards the nucleus, it will start experiencing repulsion. Accepted? So when it is
Yes, sir.
experiencing repulsion, it will retard. Retard another decelerate. It will get decelerated. Means the maximum kinetic energy of the particle zero at a per instant, where it is instantaneous. So once it comes, then what will happen is once its kinetic energy becomes zero, this nucleus will push the particle away. So it is the alpha particle is able to approach till a maximum distance, right? So it is able to travel till a maximum distance with all the kinetic energy it has before it is exhausted, and a particular point for a particular instant, right? Before it takes a U-turn of 180 degrees. So if you take that point where it is coming to instantaneous halt and measure that distance with respect to the nucleus, then that distance is what is called as the distance of closest approach. Try to break the word and see. Distance is between 2 points. It is between the nucleus and that instantaneous rest. Closest approach to another, how close that alpha particle is able to go towards a nucleus. Are you able to understand?
Yes, sir.
Are you clear or
Yes, sir. Understood.
can I take it?
Your voice is
Very good.
breaking sometime.
Voice is breaking. Okay, I'll take care. Any other doubt? Okay,
No, sir.
mathematical equation
No,
is clear.
sir.
Yeah, mathematical equation is clear, right? Simple electrostatic potential energy and basic kinetic energy formula. Equate them, get the value of R naught. That's it. Okay. So if you're clear with this, I'll go to the next part.
Clear, sir.
Good. on to the next part. Now, see, now what has happened? Rutherford had an experimental setup. So from the experimental setup, he brought in certain observations. And now, since these parts succeeded, now he has to oppose Thomson's model of atom. Right. So based on the results of the alpha particle scattering experiment, what happened is Rutherford suggested the following structure of atom. So instead of considering the atom to be a complete sphere of positive charge, we know the fact now that positive charge is concentrated at a central of size 10 power minus 14 meter, which we call it as nucleus. So atom may be a sphere of diameter 10 power minus 10. The size of the atom is still this. At a small central core called as a nucleus, and the nucleus has a diameter of value 10 power minus 14 meter. Okay, but now comes an important question. So does this structure of atom only have a positive charge? That is not possible, because if it had only positive charge, then it should have the conductive property. That didn't happen. So it should also have equal amount of negative charge. Means it should have electrons. So electrons were discovered at that point of time. Neutrons were not discovered. Okay. So what were the particles that were discovered? Electrons were discovered. Thompson proposed it already. And nucleus was proposed by Rutherford. So what did they think? Nucleus consisted of only positive charge. But neutrons came into existence later. Neutrons are a part of nucleus, which was an experiment done by James Chadwick, which we'll be seeing in the next chapter. Okay. So these electrons are there, okay, accepted that they are negatively charged particles. But how are they supposed to be? The electron is in case of the atom. If the electrons would have happened, electrons would have got attracted towards the nucleus, then there could have been no positive charge concentrated at the center. So in order to ensure that the electrons are not collapsing, the theory that he proposed was that the electrons are revolving around the nucleus in circular orbits, so that the centripetal force that is existing between the nucleus and the electron is providing the necessary, so is provided by the necessary electrostatic force of attraction between the electron and the nucleus. So what did he say? Let's conclude it again. Electrons in the atom were present, but they were not at rest, and they started revolving a circular orbit, at which point within the empty space, the centripetal force was provided by the electrostatic force that existed between the electrons and the nucleus. And the next point is, as the atom is electrically neutral, the total positive charge of the nucleus should be equal to the total negative charge of the electrons present in it. Right? So these were so this is a structure that was proposed by the observations that he got from the experimental aspects. Is it clear, guys? But unfortunately, this theory was also not right. There were some modifications made by the next scientist. But before that, let's make it clear. Is this point clear? If somebody asks you, can you explain the structure of atom proposed by Rutherford, will you guys be able to say? Yeah? Yes or no? Any doubt? Any point that is not clear? You want to go through the point? I'll give you time.
1 minute, could you wait, sir?
Yeah, I'll give you. You go through the point. If anything is not clear, please ask. Done?
I have a doubt, sir.
Please tell.
So these orbits which have been told here are just theoretical, right? So there's no experimental
Theoretically,
proof.
because nobody has seen an atom. Nobody in
Okay.
this. Okay. So whatever atom that we are learning today is only closer to the reality of some experimental observations. This cannot be observed under microscopes. You cannot see a nucleus, you cannot see atoms, everything is a proposed theory. Okay.
Okay, sir.
But is this point clear? Rutherford structure of atom, clear guys? Can I get an S confirmation so that I'll proceed?
Yeah.
Yes, sir.
Very good. Okay. Now, as I told you, even his theory was not the one which his structure of atom is not the one which we are studying today, right? That we know today, which explain more about the stability. There were certain drawbacks which are observed under his theory also. What were they? So Rutherford's model of atom offered serious difficulties with regards to the stability of atom. Following are the two drawbacks of Rutherford's model. One is the electron in the circular orbit. He told that the electrons are revolving in circular orbit around the nucleus, accepted. But the electron in the circular orbit experiences centripetal acceleration. Then, according to the concept of electromagnetic theory, what should have happened is, if you have an accelerated charges, we know what happens, right? An oscillating charge particle is an accelerated charge particle. So accelerated charge should emit energy continuously in the form of electromagnetic waves. So if it starts liberating energy, then what should have happened? When you're losing energy, what will happen? You will become weak. Right? If you keep emitting energy, then the accelerated electron should lose energy by radiation, and the energy of that electron should continuously decrease. Then the particle can no more be in a circular path. Rather, it would have got transferred into a spiral path and would have got collapsed into the nucleus. Correct? So if there was a continuous spectrum, are you guys able to understand this point alone? Do you remember what is the source of an electromagnetic wave? I would have told many times. See, let me put this question. What is the source of electric field? What is the source of electric field? If you want only electric
Positive
field,
charge, sir.
no, if you want only electric field, what will you do? If you want only electric field, what is the source of only electric field? It is a charged particle, need not be positive charge. If you have a charge itself, whether you have positive charge or negative charge, that's what we learned in electric field. No, if you have negative charge, what will happen? There will be an electric field which is directed towards a negative charge. Positive charge now, it will be directed away from the positive charge. But if you have a charged particle, it will produce electric field around it. What is the source of magnetic field? What is the source of magnetic field?
Variation in magnetic flux, sir.
That is variation in magnetic flux will generate EMF. You are getting confused. Fourth chapter, magnetic effects of current. Moving charges and magnetism. The name itself is telling you. So if you have a charged particle, and if the charged particle is in motion,
Accelerated charge particles, sir.
no. It need not be accelerated. It can be if the charges are put in motion, means if the charges are put in uniform motion also. When I say motion, it need not be acceleration always, right? The object can have a uniform speed also. So if you have a moving charge constitutes to current constitutes to magnetic field. That was the observation done by Oyster. Correct? Fourth chapter's beginning. Eighth chapter of the beginning, I would have told you one thing. What is it? If you have a charged particle, so listen to the story. Only charged particle, electric field. Charged particle at rest, electric field. Charged particle in motion, magnetic field. If the same charged particle is put under oscillation or acceleration, if you have an accelerated charged particle, that gives rise to the electromagnetic wave. Purida. So this is the basic of 8th chapter. I would have told there is a 1 mark question that they will ask you. What is the source of, at least now remember, what is the source of an electromagnetic wave? It is accelerated charge particle. Now read this point. So electron is revolving circular orbit. Correct? We know the fact that for any particle to be in a circular orbit, what is necessary? Centripetal force. Correct? Accepted? Just tell me yes or no. So particle has to revolve in a circular orbit. You need centripetal force. So force none other. Force, if there is force existing, can I say particle is accelerating? Correct? So force is not, F is equal to m beta. F is non-zero, acceleration is non-zero. So particle accelerates. So when you have an accelerated charged particle, what will happen? It will start emitting radiations in the form of electromagnetic waves. Correct? Therefore, if the energy is liberated by the electrons, then what is happening? It should lose it should lose its energy, right? Only then it will get converted to some other form. Therefore, if the accelerated charged particle loses energy by radiation, then its energy should continuously decrease. When its energy is decreasing, will it be able to be in the same circular path? Yoshibar, think about it. Will it be able to be in the same circular path?
No, sir, spiral.
So what will happen? Its radius will keep decreasing. So when it is trying to revolve in a circular path, but if its radius is continuously decreasing, then that circular path gets converted to a spiral path. So it becomes a spiral path. Thus, what should have happened? The electron at some point should lose energy and collapse into the nucleus. If that happens, then you cannot account to the stability of atom. Correct? Then how can you say that atom is stable? But all the atoms that we are able to observe are stable, or else what would have happened? There would have been a continuous reaction taking place around us. Correct? And secondly, according to the classical electromagnetic theory, the accelerating electron must radiate energy at a frequency proportional to the angular velocity of electron. That is what I told you already. So if an electron is accelerating, right? So it is basically oscillating. So when you talk about an oscillating charged particle, it has a frequency associated with it. Purida. So an oscillating charged particle will have a frequency associated with it. And there is an electromagnetic wave coming out from an accelerated charged particle that will also have frequency. So who is deciding the frequency of this electromagnetic wave? It is the frequency with which the electron is vibrating. Now relate the point. The accelerating electron must radiate energy at a frequency proportional to the angular velocity of the electron. Okay. Therefore, as the electrons spiral towards the nucleus, the angular velocity tends to become infinity, and hence the frequency of the emitted energy will also tend to infinity. This will result in what? This will result in continuous emission spectrum with all possible wavelengths. But we know, as I told you, in Bohr's model, you will be studying about the emission spectrum of hydrogen atom of different spectral lines. But experiments reveal only line spectra of fixed wavelength from atoms are possible. So try to read this point. If there is any doubt, ask me. So what are the points? How do you take the bullet points from it? According to the classical electromagnetic theory, what should happen? If you have an accelerating electron, then that accelerating electron will have a frequency associated with it. And that frequency is proportional to the angular frequency of whom? To the angular frequency of the electron, which is oscillating. Now, if the radius of the spiral path is decreasing, then its angular velocity will increase, because angular velocity and radius are inversely proportional to each other. V is equal to r omega, omega is equal to V by R. So radius decreases, omega increases. So when the radius is going to decrease, the value of omega will increase. And when the radius becomes 0, omega will become infinity. When omega becomes infinity, what will happen? The frequency of the emitted radiations will also become infinite. Means there will be a continuous spectrum. See, continuous spectrum, nothing to worry. You know what is a rainbow, right? You know how rainbow looks like. Right? Different colors are going to get emitted. So imagine something of that sort is going to happen continuously forever. If that would have happened, right, everything surrounding, you will not be able to see white light at all. Everything around us would have been continuous spectrum, because every atom would have started doing this. But that is not happening. Right? So that is also a serious problem that was existing as a part of the drawback of Rutherford's alpha ray scattering experiment. But one fact that got revealed is See, one point where he could knock out Thompson's model is stating that the positive charge is not present throughout the nucleus, so throughout the atom, rather it is concentrated at the center. But the issues he faced is with respect to the position of electron. So in both the cases, if you see, the electromagnetic wave theory actually collapsed it. Are you able to understand? Guys, yes or no? Is it clear?
Yes, sir.
Right? So that's what happened. Now, the question is, since he faced difficulty, there should have been some other scientist who gave us a concept of stable atom. That was done by Niels Bohr. So in the year 1930, Bohr modified the Rutherford's model of atom in order to explain the stability of atom and the emission of sharp spectral lines. So see, this sharp spectral line is not a big thing, guys. Have you learned about emission spectrum in your chemistry? You know what is emission spectrum, right? What happens? When an electron jumps from a higher orbit to a lower orbit, energy is dash. Tell me, fill the blank. When an electron jumps from higher orbit to a lower orbit, what happens to the energy? Is it released or is it absorbed? Is there any problem from my side in communication? Is my question clear or not? I'm asking something which you already. I'm asking you something which you already know. There is an electron which is in a higher orbit, and from that higher orbit, it is jumping to a lower orbit. Is the energy released or absorbed?
Release, sir.
Release.
Yes, that's what is called a. So energy is released, right? So that released form is what we call it as emission spectrum. So in emission spectrum, depending on where the transition, between which orbits the transition is taking place, I'm sure you would have heard these terms called as Lyman series, Balmer series, and all those things. Yes or no? Have you heard these words?
Yes, sir.
Right, you have heard, right? So that is the point they are trying to say. Experiments revealed that only line spectra of fixed wavelength from atoms are possible, which was solved by Bohr. But Bohr also had some serious drawbacks. Later, other scientists came, but that will not be discussing as a part of physics. Okay. So, in 1913, Rutherford's atom of model, in order to explain the stability of atom and the emission of sharp spectral lines. So, he proposed the following postulates. These two are very important. So, listen to this. Rutherford told electrons revolve in circular orbits. That is accepted. But Bohr modified it, saying that an electron will revolve in circular orbit, but it cannot take a random orbit of itself and revolve. Rather, so that's what is given. See, an electron cannot revolve around the nucleus in all possible orbits. Rather, it will revolve only around the nucleus only in those allowed or permissible orbits in which the angular momentum of the electron is an integral multiple of something called as h divided by 2 pi, where h is Planck's constant. Okay. And those orbits in which the electron is revolving are what are called as stationary orbits or non-graduating orbits. And the electron revolving in these orbits will not radiate any energy. So where did Rutherford fail? He told that electron revolves in random orbits, and because it is revolving in random orbits, it radiates energy. But that didn't happen here. What happened? It will revolve only in those orbits where the angular momentum is quantized. And what is the name of those orbits called as? It is called as stationary orbits or non-graduating orbits in which energy released is zero. Is that clear? Suppose if you take m and v as the mass and velocity of the electron in that permitted orbit of radius r, then the angular momentum of the electron is mvr. That mvr is equal to n into h by 2 pi. Mvr is called as the angular momentum. H by 2 pi is the constant multiplied with n, where n is the orbit number or the principal quantum number, which has an integral value starting from 1, 2, 3, so on. right? This condition of MBR is equal to NH by 2 pi is what is called as Bohr's quantization condition. What is it called as? It's called as Bohr's quantization condition. Okay. Secondly, what happens is an atom radiates energy. Atom radiates, not absorbs. Radiates means liberation. An atom radiates energy only when an electron jumps from a stationary orbit of higher energy to an orbit of lower energy. Suppose if an electron jumps from the orbit of energy E2 to an orbit of energy E1, then that E2 minus E1 will get corresponding, will give the corresponding value of energy of the radiation that has come out. And that radiation is basically a photon. It's an electromagnetic wave. So E2 minus E1 is equal to h into nu, where h is Planck's constant, nu is the frequency of the radiation that has got emitted. So E2 minus E1 is equal to h nu is what is called as the Bohr's frequency condition. What is it called as? It's called as the Bohr's frequency condition. Okay, so what are the two conditions proposed by him? One is called as Bohr's quantization condition, and the second is called as Bohr's frequency condition. Did you guys make a note of it?
Sir, so the formula for frequency conditions E2 minus E1, sir.
So E2 minus E1 is equal to h nu, where E2 is the energy of higher orbit and E1 is the energy of the lower orbit.
So here E is half mv square, sir.
No, no, no. That is not kinetic energy. That E we will derive, don't worry. See, what did Bohr say? You have a nucleus, right? Try to understand. So around the nucleus, you will have orbits. I'm sure you're clear of this orbits concept, at least from your chemistry. We'll talk about the shells and all, no? K shell, L shell, M. So you have these orbits, no? So in the first orbit, you will say you will have 2 electrons, second orbit, 8, the octet rule and all comes into picture. Those are all orbits only, right? So
yes,
when electron is revolving, so what did Bohr say is electrons cannot revolve. Electrons do revolve around the nucleus, no doubt in that. They are not at rest. But they revolve only in those particular orbits with where the distance from the nucleus should be in such a way that in those orbits, the angular momentum, that is m into v into r, should be equal to n into h by 2 pi. Only if this mathematical condition is solved, then the electron is allowed to be in that particular orbit. Means r should satisfy that condition. You're able to understand? That is the meaning of Bohr's quantization condition. Now, what will happen is, it is not like every electron has only one orbit. It can have more than one orbit. So suppose you have the second orbit and the electron is here in the second orbit. If the electron is jumping between the second orbit and the first orbit, means it is jumping from the second orbit to the first orbit, it will start releasing energy which is equal to h nu. Correct?
yes, sir.
So that is what you told about emission spectrum. So if I say the energy of the electron in the second orbit is E2, and if the energy of the electron in the first orbit is E1, then E2 minus E1 is what is equal to h nu. That is what is called as Bohr's frequency condition. Yeah, frequency, no? Because we are taking the frequency. Frequency is the frequency of that energy that is getting released. So try to understand. E2 is the energy of the electron in the second orbit. E1 is the energy of the electron in the first orbit. And that E1 and E2 are not kinetic energy. It is not half mv square because the electron is revolving in the nucleus. Sorry, revolving around the nucleus. When it is revolving, it has kinetic energy. Along with that, it also has a distance from the nucleus. So it will have potential energy. So the energy that I'm trying to talk about for the electron is the sum of kinetic and the electrostatic potential energy. Purida.
Yes, sir, yes, understood.
Now you understood? Okay. So it is not because I understand where you're coming from. You're seeing too many equations with respect to half mv square and electrostatic potential energy. For you to have a clear-cut differentiation, you need to practice them, right, and see, so that you will get more doubts and things will get clarified. Okay. So this is all about the Bohr's quantization and the Bohr's frequency condition. Sharia. So the next point that we are supposed to see is we need to derive the radius of those orbits in which the electrons can revolve, and we need to derive the expression for energy of the electron in that particular orbit. Then we will see the other stuffs. Okay. So what I will do, I'll stop with this because you need some time to revise these concepts first. So there are only 3 subtopics that are left out, which we can complete it comfortably in the next class. Don't worry about it. Okay, those 3 are derivations only. So apart from this, is there any doubt that you have?
No doubt, sir.
Okay, what I will do is I'll share this notes. In the meanwhile, during the week, you guys try to write down. In the empty space is there, no? This part, this derivation I've already written. Okay, you copy those derivations and have it ready so that when I teach you in the next class, you will understand it better. So once this is over, we can go to the next chapter directly. That is nuclear. So this will, I think, this will take around 45 minutes. Let's take 1 hour itself. No, next class. What is the big deal? Okay, so next class I'll finish atoms. Tuesday I will start nuclei, and Wednesday I'll finish nuclei, and the following Monday, that is 21st of this month, I will take semiconductors, and Tuesday will come close it. With that, this year's syllabus will be over. Clear? So in the meanwhile,
Yes.
it is expected that you guys keep preparing, as I mentioned. So that's it from my side for today, guys. We can wind
Thank
up
you.
if there are.
Thank you.
Thank you, sir.
Sir.